just from general grounds what the structure of the energy momentum tensor should be under this set of assumptions. And the set of assumptions were that basically we just had isotropy in momentum space. That's all you need to write down this form. And once you have that assumption, there's only the fluid floor velocity, which I remind you is normalized always such that u dotted into itself is equal to 1. We only had that, so we could construct a bilinear from it, and we had the metric tensor itself. In my convention, we used the mostly minus metric. If for some reason you were traveling yesterday and you didn't get to see the first part of my presentations, everything is available here at this URL. So it should forward you to a Google Drive folder with everything in it. Good, where hopefully I define everything properly. The nice thing about this decomposition, we're going to use such decompositions going forward as we go all the way to anisotropic hydrodynamics, is that this is a general now Lorentz structure, but these coefficients that are sitting out here are Lorentz scalars. So they're the same in every frame, and we can compute them in whatever frame we like. And what we did yesterday was show that these quantities, P and epsilon here, were nothing but the energy density and the pressure in the local rest frame of the fluid. So the fluid might be moving to the left here in the room. We boost ourselves, so we're co-moving with the fluid. We measure the energy density and the pressure in that co-moving frame. That's what P and epsilon are. But now in any frame we like, we can now obtain the general expression for T mu nu. So once we had that general expression, it was a sort of calculus exercise to go through taking derivatives of this expression. We got derivatives of P's, we got derivatives of U's, and then we took projections in the first case with the fluid floor velocity itself, and we got an equation that looks like this, written compactly, where capital D is the co-moving derivative, theta is the floor divergence of the fluid floor velocity, which are summarized over here. And then projecting with this transverse projector, which projects vectors orthogonal to the fluid flow velocity. So if your fluid's flowing this way, you're projecting things transversely, and you can define derivatives transverse to the flow and so on. This is the derivative transverse to the flow. And then we were able to get another equation. So I in the second equation was space-like, it's 1, 2, 3. So we had 4 equations sitting here. As we discussed, we needed some additional constraint equation in order to close these, because there's 5 unknowns, there's epsilon P and the 3 independent components of UI here. So we needed some additional constraint. So traditionally people say at this point you have to invoke the equation of state. But as I pointed out yesterday, if you truly had a conformal system where epsilon was always 3p, that relation holds out of equilibrium as well. So really you should think of it more as some additional constraint that you need to apply. It could even be a non-equilibrium constraint that comes from someplace else. Good. Then we made it even simpler by looking at a very special case, but it's the special case that's relevant for the sort of asymptotic limit of heavy ion collisions. So the case in which your nuclei are the size of neutron stars, or an infinite size neutron star, and we're accelerating them at the speed of light towards one another, and we can ignore all the masses in the problem because the energy scales are so high that none of it really matters. And in that case, the equation of state can be approximated as conformal, so epsilon plus p just becomes 4/3 here. Theta became a 1 over tau in that special limit, and the second equation became trivial because there were no, we used a special coordinate system called Milnor coordinate system, and in Milnor coordinates there were no gradients. So we had to find a special coordinate system where the flow became static. And in that case, we could write down a simple ordinary differential equation. This d thing, the co-moving derivative in a static flow, just becomes the time derivative. Good. And in that case, we could just solve that ordinary differential equation, and we could get the full time evolution in the forward light cone of the energy density. And I said something slightly wrong at the end of last lecture that Vincenzo quickly corrected. I said, well, you know, if it wasn't, this was the case for conformal, that 4/3 comes directly from here, and it came from the fact that epsilon plus p was just 4/3 epsilon. And that's tied to the fact that in a conformal system, dp de, which is the speed of sound squared, is simply 1/3. And if I had a different speed of sound, my claim was that you could write the temperature, but I said it incorrectly. I mean, this equation would change if it was non-conformal, so it had a different than 1/3 speed of sound here, and if it was constant speed of sound, then it would become this. But the relation that I wrote for the t, I think I wrote a t to the cs squared. That's not true. This is true, but then you would have to go through some more complicated manipulations using some Bessel functions to get t. But anyway, so that's the starting point. And the foreshadowing from yesterday was the following, that in general, we can decompose T mu nu into some ideal part, which in the end, it started with 5 degrees of freedom. Applying this conformal constraint or equation of state, however you want to think about it, this thing has 4 degrees of freedom. Over here in general, because this is a rank 2 symmetric tensor, this has 10 independent degrees of freedom. And philosophically, since nothing is ideal in life, we've all learned this through living through COVID, we have to add an additional COVID term to the equation, pi mu nu, which represents the non-ideal corrections to this. No, if pi mu nu is 0, everything's good, you know. This represents the non-equilibrium corrections. And in principle, it should contain 6 new degrees of freedom. It's not exactly obvious. We're going to step through why that is the case now. Because it's also, because T mu nu is symmetric, it has to be symmetric. But if it's just a full rank 2 symmetric tensor, it should also have 10 independent degrees of freedom. So there's an additional constraint that's going on here, which we will discuss next. Good. So first of all, we make a choice, and in hydrodynamics lingo, this choice, oops, I wrote it wrong again, is something called the choice of the frame. And we're going to use something going back to Landau, which is called the Landau frame. And we're going to require that if we come in here with u mu and we hit T mu nu, that it simply returns epsilon times u mu nu. Now that's obvious from this form. If I come in here with u mu, this will just give me a u nu. I'll get a 1 from here. The p's will cancel. I'll just get epsilon times u nu back, right? But now we're just going to require that that quantity epsilon is the you know, the equilibrium energy density, or whatever this leading order approximation, whatever you want to call it. Some people call it epsilon naught. I'm just going to call it epsilon here. But we're going to require it in general, not just in this special case. But what that means in practice, if you hit this new equation, is that the following has to be true. That we get a set of 4 equations for pi mu nu, because there's nu runs from 0 to 4, which turn those original 10 degrees of freedom now into 6 degrees of freedom. Now in the local rest frame, what that means is that pi mu nu will have zeros here, and then it will be a space like rank 3 tensor that lives down here. But that space-like rank 3 tensor has to be symmetric, therefore it has 6 independent components. So that's where this 6 comes from up here. Good. Good, so now we have all the counting complete. So now, as I said yesterday, we had derived 4 equations. In the end, we're going to need 10 equations if we want to evolve the full non-equilibrium T mu nu. So somewhere we're going to have to find 6 additional equations. And they're not going to come from conservation laws because we used all the conservation laws already. So they have to come through some microscopic dynamics, which means some model. But it turns out there's a sort of universal limit where you can write these things down, and that's something called the Navier-Stokes limit. Going back to the 19th century. Sorry, yeah, 19th century, I think that's right. And the basic idea in this limit is the following. I can take this tensor and I can decompose it into 2 pieces. And I'll try to be very careful when I write it on the board. If it's a capital pi mu nu, that's the total viscous tensor. If it's a smaller case squiggly pi, that means the shear tensor. If it's a capital pi with no indices hanging off of it, that is the bulk viscosity, or the bulk viscous correction in this case, I should say, sorry. And this was our friend, the transverse projector. So just to make this explicit, in the local rest frame, what does this look like? And I'll just write the space-like components because, as we see over there, those ones on the left and right, here and here are 0, so we don't have to write those. And I'll just write the diagonals in this case. And then we can guess the rest. And I'm running out of space. And then there's a bunch of other elements here, which you can fill in with your brain. But what's most important, that's the reason I wanted to write out the diagonal, is that we can see that pi is encoding corrections to the pressure that are going to break the isotropy. And in general, if pi xx is not equal to pi yy, you're going to get a different pressure in the x and the y direction. Capital pi is a bulk viscous correction. It affects all directions in the same time, so it doesn't break the isotropy. It affects the pressures the same in each of the directions, and that's just due to this decomposition here. Now, there's another constraint. If you want to write it this way, you have to have another constraint because remember, we still need 6 degrees of freedom. So the other constraint is we're going to make this part traceless. So that it only has 5 degrees of freedom. And then this part, as you can see, if little pi is traceless, that means in this case pi xx plus pi yy plus pi zz has to be equal to 0. And then the trace is just 3 times capital pi. So we've just shifted the trace into this thing. So it's just a rewriting of the original tensor, but it turns out to be physically important. The reason that it's physically important is because this correction, as we'll see, represents the response of the system to uniform compression or decompression in all directions simultaneously. So imagine I have a sphere and I'm just compressing it uniformly. That's this viscous correction. So the heating that you would get from such a compression-decompression cycle is encoded in here. Whereas this guy, the traceless one, is the one that it gets from the shear. So if I take my thing and I start doing this to it, right, in my box, and I do like that, and I get some heating from doing that, instead of just stretching and squeezing it uniformly. And the mathematical decomposition is to just break it into a traceless part and a traceful part. It's a unique decomposition. Good. Now, we had written down equations 1 and 2 in the ideal case. Now, if we incorporate this correction, we can just, and I won't go through the exercise now, but you can imagine in your head taking a derivative of this, you get the old terms that you got from here, you'll get some new terms from here, right? And I'll just write down the final result now. Okay, that's what we had before. Where I've introduced yet another hydro notation that allows us to write the things compactly, and that in general is if I have two vectors, it's just the symmetrized version. Probably should have chosen different indices here. It's confusing me even. So this notation with parentheses means just the symmetric version of that. And if you just work through the math, you'll find that that's what happens. So we get these two new equations of motion, but again, we don't know what pi is, so we can actually update these equations of motion. We can write it down, but now we need the equations of motion for this guy that they're going to couple to these two equations. Now, in this Navier-Stokes limit, which I'll just write as NS, we start by writing down sort of physics definitions called constitutive relations. And Francesco discussed these a bit yesterday, how you can get them. I'm just going to write them down as physics definitions to begin with. Now, in general, before writing down their definitions, I'll note that this thing, whatever it is, it has to be proportional to gradients in the system. Because remember, if there's no gradients in the system, we're in thermal equilibrium. Nothing moves left and right, we're in a static situation. So whatever this thing is, it should involve, in general, some sort of tensor of gradients of the fluid flow. But we can break this tensor, like we did here, into a traceless and a traceable part into 2 bits. And we're going to break them exactly into these 2 bits over here. And this thing is given a special, well, let's just write it. So because our system might have different responses to these two different ways of deforming it, either the shearing or the compressing, we can decompose that general d mu u mu into two kinds of motions. One is this purely the divergence of the fluid flow velocity, which is this stretching or squeezing uniformly in one direction, right? If I take an integral of this, it's just a stretch or a squeeze. Then there's some new special notation. These things are angle brackets up here. And the angle bracket is not very intuitive, but what it does is it projects out the traceless part of d mu d nu. Let me just write up the definition of what it is up here in the corner. So that's a notational definition. And the only thing that's doing is taking this sort of general derivative and subtracting out this bulk deformation part. Right? This is the traceful part. We're just subtracting that out so we can isolate physically these two different kinds of ways to deform the system. And because the system might react to these two different ways of deforming it differently, we introduce these two different transport coefficients. One is called eta, which is the shear viscosity, and the other one is zeta, which is the bulk viscosity. Now, if it's a conformal system, that means it also has some sort of dilatation symmetry, right? The scale doesn't matter. So if I stretch or squeeze it uniformly, nothing will change. So this bulk viscosity goes to 0. So in a conformal system, this goes away, and you only get left with the shear viscosity. But in general, if in a heavy ion collision, you have to include both. And these are only the first two transport coefficients. In general, there's a lot of transport coefficients hiding. These are just the first two that pop up at first order in the Navier-Stokes limit. Yes?
I'm completely out.
Yeah, okay.
The question might be, is this a kind of perturbation theory approach in which you try to look for the main effect?
Yeah, so you can think of it as a perturbation theory in gradients, right? So you're going to start by a small deformation of the system, and then you're going to write down the correction to this. But yeah.
So you look for the main effect and try to separate the smaller effects or not?
We're going to write down the more complicated versions of this as we go, yeah. So, but right now it's not really perturbation theory, it's just decomposing tensors into their sort of fundamental structures so that we can identify the physics. So far we haven't said whether eta or zeta are big or small or anything. They're not dynamical right now because they're totally written in terms of the fluid flow velocities. And as a result, if you were to just take these guys, as written right here, plug them into here, you'd get some new set, some updated now version of these equations, which in the non-relativistic limit just reduce to the Navier-Stokes equations for fluid flows, which mathematicians have been struggling with since, 100 years. This would be the relativistic generalization of Navier-Stokes. But the bad thing about the relativistic generalization of Navier-Stokes is you'll find that these equations are parabolic and acausal. So you have to go further than these. So if you just take these two relations, plug them in here and here, write pi out, plug it in here, you'll get a mess. You'll violate causality. So something else had to be done. And that something else started in the 70s with Mueller, Israel, and Stewart, and we'll come to that in a second. And that was mostly in the astrophysical context because they needed to describe astrophysical relativistic plasmas. But then it was not really recognized in the heavy ion community until, I think, 2003 in the end, and it was Asmodini Moronga in Frankfurt who then brought the new formalism that fixes this causality problem to the heavy ion community, and then it took off like wildfire. But before we go to how to fix the problem, so just to state again, The problem is that this set of partial differential equations is parabolic and acausal. But before we go to that, we can get some sort of intuition for how adding these corrections is going to change things in terms of the components of T mu nu. And I'm going to focus on the shear correction, since it's the most important one, and I think most people would agree, in heavy ion collisions. So we're going to go back to our old friend, conformal Bjorken flow. That's the reason we had to learn what it was, because we're just going to use it as a touchstone every once in a while to set our expectations. Good. Since it's conformal, as I mentioned earlier, the bulk viscous correction is 0, and we can ignore it, and that's nice. Now we can focus our attention on pi. Remember, Bjorken flow is homogeneous in the transverse direction, so it's transversely homogeneous, and it's also boost invariant. So as a result, because it's transversely homogeneous, there can be no symmetry breaking in the xy plane. So that means that whatever here is here, if there are some viscous corrections, they have to be exactly the same in the xx and the yy directions by symmetry. And I'm going to define this, and it's not exactly going to be clear to you why. I'm just going to call it a scalar pi. That's not the number pi, it's just a scalar that represents those two guys. And the factor of 2 should become obvious in a minute why I do that this way. Now recall that this pi thing is traceless. So that means in practice, once I know what pi xx and pi yy are, I can write down what pi zz is, right? Because pi xx plus pi yy plus pi zz has to be equal to 0. So this immediately tells me in this notation that pi zz has to be equal to minus pi, this scalar. And that's right, and I put that factor of 2 in there because I wanted the zz component to be the simple one. Yeah, these are the matrix components, x, x, and y, y. Let me write it out in the local reference frame. So to the left. Oh, sorry, that's ZZ. Thank you. Brain fart. Better? Sorry. Good. Good. So if I write out this now pi mu nu tensor, well, let's just write pi ij. I don't like to write the whole thing. It's going to have the following form in Bjorken flow: pi over 2 minus pi, and then it's going to have zeros on the off diagonals by symmetry. Good. Now going back, where are we going back to? I erased the equation. In general, the full energy momentum tensor was this ideal piece plus the full viscous energy tensor, viscous tensor rather, and in this conformal case, that's just pi mu nu. So now let's calculate what the full energy momentum tensor is for Navier-Stokes subject to conformal Bjorken flow. So I can define, let's do it this way, the longitudinal pressure as the ZZ component of the total energy momentum tensor. That's what I'm going to call the longitudinal pressure. And of course, it's the equilibrium ZZ component. And as we've just learned, it's going to be plus pi ZZ, which is simply the pressure minus pi. Now, of course, this sign convention that I've chosen here for pi is a convention, and the factor 2 is a convention. So I like the pi. I like the minus here, but other people might do something. Yeah, you should really call it eta eta. Yes. Yeah. So if you want to be strictly true, this should be eta eta. You're right. But I just write it as ZZ. But you're right, so I'll fix it. And likewise, you can get PT, and now I won't be wrong. You can write this as TXX, right? So it's going to be the equilibrium TXX plus pi XX, and it's going to be P plus pi over 2. And in this case, you can evaluate TYY or TXX. There's a symmetry, so it doesn't matter. You'll get the same answer. And then we can immediately write down this pressure ratio, the thing that I was plotting over and over again yesterday. It's the pressure minus this pi over pressure plus pi over 2. And this is in the Navier-Stokes limit. Actually, this is actually general for Bjorken flow, so I don't need to write Navier-Stokes yet. So that's general for Bjorken flow. The transverse pressure is independently either XX or YY, I think, in this notation. Yeah, in my notation, it's either XX or YY. So I just take the total, just focusing on Tij. I write it as PT, PT, and PL in this case. Just to keep it simple, so if I know that it's isotropic, then these three things are equal, and I don't have to worry about factors of 2. But the factors of 2 pop up in other places, like here. You can never get rid of the factor of 2. Now, as we're going to see in a few seconds, pi is for Bjorken flow is a positive quantity. The viscous correction that you get, and so its action is to reduce the longitudinal pressure and increase the transverse pressure. So already starting from this, in the early times in a heavy ion collision, we can see that PL over PT is going to be some number less than 1, just by looking at this, because pi is greater than 0. Now in other systems that might change, but for our heavy ion collision, this is going to be the case. So let's work out what it is in the Navier-Stokes limit explicitly. Good. So for Bjorken flow, the fluid velocity profile looks like this. Remember, it's just a boosted static flow by some rapidity eta. Where now I'll write the inverse relations. that define eta and tau. They're nothing but what we call the longitudinal proper time, because it only involves t and z, and that's because we reduced the dimensionality of the problem here, and the space-time rapidity, which is this angle in the forward light cone. Then, in order to calculate this little pi thing over here, in order to get the correction to the pressure, we need to go back to this defining relation that's up here and compute this angle bracket derivative of the velocity. So that's what we'll do next. So that's what it is in general, at least in the first order Navier-Stokes case. So I'll put a little ns here. Because there's really only one independent component in here, we only have to compute one of them, and once we know one, pi xx, pi y, we'll know the rest. So we'll just compute pi xx. It's the easiest one. So there's the eta out front, and then we have to refer to that definition that's way up there in the upper left-hand corner. Sorry for the squeakiness. All right, so that's what it would be in Bjorken flow, except for, what's this term in Bjorken flow? 0y. Yeah, because ux is 0. Good, I'm just making sure you're paying attention. That one's 0 because there's no flow in the x and the y directions. I've gone ahead and written that forward divergence of the flow that's up there in the upper right-hand corner as theta. What is this in Bjorken flow? 1 over tau, thank you. What's this? Delta xx? -1, good. In the local rest frame, which is good enough for us. So in the end, this is 2 eta over 3 tau. And as I said, by symmetry, that's also pi yy. And by the tracelessness, we can immediately write down what is pi zz. It's -4 eta over 3 tau. And with that, we can now write the actual Navier-Stokes form of this relation. So PL over PT in the Navier-Stokes limit is P -4 eta. How do I want to write this? 4 eta over 3 tau, P plus eta 3 tau. Okay, now discussion. So what does this formula tell us? Why were we so interested in it? So what it tells us, as we can see here, as let's imagine we're working in the case where eta is fixed, so a fixed shear viscosity. You could even imagine fixed shear viscosity to entropy density ratio. It doesn't matter for the next discussion. And I start going earlier and earlier in time. So I want to initialize my system earlier in time. So eventually, this term will become bigger than this one. And that means, and because this is positive, this is a positive number by definition down here, this whole thing will go negative. So eventually it will break, right? Because the pressures went negative. What the heck does that mean? And you can establish from this, and it's written in the notes, I won't go through it, a kind of lower limit on when you should trust Navier-Stokes. Because when the pressures go negative, you should stop trusting it. But it contains this sort of seed of that cartoon that I was throwing around on the slides last week, or yesterday rather. I've lost track of time, which country I'm in. That if I plot the pressure ratio as a function of time, in the limit tau goes to infinity, these terms are ignorable. I get P over P, it goes to 1. But then at some point in time, it will actually go negative. And real solutions to real hydro or kinetic theory in practice do something like this and approach this Navier-Stokes solution at late times. But it already tells us that even in the late time limit, we're going to have some pressure in isotropy. Now, it might be small enough that we can ignore it. We're all physicists. We like to make the spherical Cow approximation. But it's there. Philosophically, it's always there. You have to take it into account. Good. So if you look in the notes, I go through like how do you even calculate this time where it goes negative, and you can then check it against the plots that I showed you yesterday, and you'll see that it exactly gets it right when the plot goes negative. All right. Now, it's an academic result because the equations up here had this big problem that they're acausal. So maybe, you know, if I fix the causality of the problem, I can fix this problem. Turns out the answer is no. You can generate a causal version, you're still going to get negative pressures down here. But you'll get closer to the exact solutions if you do it. It'll just go negative at a slightly earlier time, so you'll be able to push the solutions a little bit back further in time. But as a matter of principle, this is bad, so we need to fix it. Questions before I go on to the next part? Well, you could. I mean, it is certainly a lower limit that you can't apply first order viscous hydro below that time, right? But it still doesn't tell you that it's valid at that time. So it's a lower limit. So the validity is above that. I would say, I would agree with that statement, yes. But as we'll see when I go back to the presentation mode on Friday, it takes a while. Usually this is on a log scale when I show it, so it doesn't seem like a while, but it takes a while for the real solutions to converge to the Navier-Stokes limit. That's a good question. I'm trying to do the conversion in my head. It's roughly 1.2 Fermi, it's in that ballpark, yeah. It's in that ballpark. So yeah, if you really want to try to cover that first Fermi over C, yeah, you shouldn't use this. And well, there's another big reason not to use it up here, which upset people even more. And when you fix it, this thing also happens down here. Now, the other statement is that, which I guess I should have pointed out from this general statement, this general expression here, is that the problem gets worse as eta gets large. Right, so exactly where this thing happens also depends on eta in your simulation. So if eta is big, then this breaks at earlier times. If eta is 0, it's perfect always, it never breaks, but eta is never 0. So in the analysis I did in the notes, I tried to scale it to rewrite it in terms of the shear viscosity and establish the limit generally, but it's not particularly relevant. Now, the reason I was very interested in this, well, because, 15 years ago, people were saying, eta has to be small, but then they were applying viscous hydrocodes at large eta, and I'm like, well, it breaks. If I take eta to 10 here, you can't start your hydrocode until like 5 Fermi over C. But they're running a hydrocode when eta was 10. So then that started a whole long investigation of like, how could you improve hydro to get it down here reliably into the low, even for large eta? And in the end, we invented anisotropic hydrodynamics, which works at eta's infinity, which is great. It has the free streaming limit. All right, that was an aside. So we went beyond the ideal limit, and we went one baby step forward to Navier-Stokes. How do we go beyond Navier-Stokes? Now, the fundamental problem, the reason that these equations are parabolic, is because this shear viscous correction responds immediately by the constitutive relations to any changes in the fluid flow velocity. So if I have some fluid flow velocity, I immediately get a viscous heating from that. Immediately. There's no causal delay. And so that's what that drives these equations acausal in the end. So it has an instantaneous response. And anytime there's an instantaneous response to something, can I spell instant? Einstein tells me, well, going back Mach, Lorentz, his people before him, everybody would, jump at you and say nothing's instantaneous, so you probably need to go back to the drawing board. Good, so the simplest way to fix this sort of sketch-wise would be to do the following. I'm going to introduce some time scale, which I'm going to call the shear relaxation time scale. And I'm going to write down a co-moving derivative equation for this. Now remember, if it was special, you can sort of think of this as a fancy time derivative, right? So this is telling us how pi mu nu evolves in time in a fancy way. So the simplest thing I could do if I was a modeler, right, is that I would posit an equation like this for pi mu nu. That there's a new time scale that makes it not instantaneous. If I was in the local reference frame, this would just be tau, d tau, pi, plus pi is this. Now in the limit that, that tau pi is 0, so I have instantaneous relaxation, then I just get back my constitutive relation again. But when tau pi is finite, what this is just it's a kind of relaxation equation that whatever initial condition you choose for pi, it will relax on a time scale of the order of tau little pi to this Navier-Stokes result. And by introducing this time scale, you can then restore causality. And you can do a similar thing for the bulk viscous correction. And there's another one, that's a capital pi. And if you look at this sort of model-based kind of equations, you'll see that given some constraints on the relation between tau pi and eta, so there's some algebraic relationship that sets a lower bound essentially on tau little pi and tau kappa pi. As long as you're above that bound, the equations are causal. And you're happy relativistically. And this would provide now the update equations for this capital pi, which is the sum of the little pi in this guy times delta mu nu. And then I would solve that set of equations together with this one, and I would evolve them forward in time. And that would tell me how to get the full non-equilibrium evolution. Now, the problem is that, to use a technical term, I just pulled these out of my butt, right? I just like, these look good equations. Let's use those, which is not a bad thing to do in physics sometimes, you know, but there's a systematic way to get them, and I'm not going to go through the systematic way. There's an expert back in the back row up there, Gabrielle, who's been trained by the master, another Gabrielle, Denicol, in how you actually derive the complicated form of these equations, which is much more complicated and verbose than what's written on this board here. And I flashed them yesterday in the slides. They took up an entire slide in a tiny font. You remember those ones? Yeah, they're not pretty, so we're not going to derive those. It takes years, and we don't have years. Instead, I'm going to ask you to go ask Gabrielle later, and he'll show you the entire derivation. I'm sure he has it written down. I will write down in a very special case, which again is, well, this is a new special case. So we've had Bjorken flow and conformal stuff. I'm going to write a new special case down. Again, I have a kind of tie to kinetic theory, and if you go through Gabrielle Denicol's work, that's how those hydro equations were derived. It was by taking the Boltzmann equation, doing something called a dual expansion in the Knudsen number and the inverse Reynolds number to second order. And basically they repeated this Mueller-Israel-Stewart calculation from the 70s, but did it right. Mueller-Israel-Stewart did not do it correctly. They did not include all of the second order terms because in the Mueller-Israel-Stewart paper, they were more interested in kind of astrophysical applications where this fluid flow divergence wasn't diverging and going crazy, so they could just ignore some terms, and that was probably a good approximation for them. But in heavy ions, Mueller-Israel-Stewart is just wrong. And DNMR fixed that. Now, they've written it down in a general case starting from something called the Boltzmann equation, which describes the evolution of the one-particle distribution function. In general, there's some collisional kernel that depends on the distribution function and includes 2-to-2 scatterings, 2-to-3 scatter, you know, all the possible scatterings you can imagine should be included in over here. And when you start doing the systematic procedure, you can start writing all of these transport coefficients like eta and zeta as certain integrals of the distribution function. We're going to keep our life simple and write a sort of toy model of this, which is called a relaxation time approximation. And the reason for doing so is twofold. One, it makes our lives easier and we can actually write down the equations on one board in that case. But also, as we're going to see going forward in the lectures, in this case of relaxation time approximation and the Bjorken flow, you can solve this problem exactly. And we'll go through how you solve that problem exactly. But then we can start testing different things in relaxation time approximation. We're going to start now building up a sort of set of results that apply in this approximation. So what is relaxation time approximation? I should define it. Relaxation time approximation is sort of poor man's collisional kernel. One thing that we know about this collisional kernel here on the right is that it has to vanish in equilibrium. So our poor man's version of this would be that we just make it linear in f minus feq, so that if f ever becomes an equilibrium distribution function, this thing just goes away. We introduce some time scale, which I'm going to call the relaxation time. You're going to raise your objection now? Oh, I forgot the PMU. Thank you. I did something terrible wrong here. Yes, sorry. My brain doesn't work sometimes. Thank you. Good. I also did the same thing in the notes, so ignore the notes. This is right, thank you. So this is P mu d mu. Okay. Anyway, so there's some relaxation time. If it's a conformal system, there's only one time scale around, and this thing has to be proportional to the 1 over the temperature, and that will come up again. If we were thinking about solving this in the local reference frame or in Bjorken flow where everything is simple, P dot U, where U is static, this is just the energy sitting there, P naught. Good.
Sorry, small question. Shouldn't be G explain the principle by copying? Or is it?
Well, I said proportional, so there can be a number up here. It can be there can be a coupling constant up there. Yeah, and it should be proportional to. Yeah, so normally it's 5. Conformal RTA, it's 5 eta bar over T, where eta bar is eta over S. And the shear viscosity goes like the coupling to the 4th. When the shear viscosity goes to 0, the relaxation time goes to 0. When the shear viscosity goes to infinity, the relaxation time goes to infinity. So those are the ideal and the free streaming limits. But yeah, I was trying to just write the proportionality. But in general, for any collisional kernel, this is the right result for RTA. There's a 5 sitting there, not a 6. It's very important. I argued with the referee over this for many years. It's not 6. Good. And even in this case, I'll attempt to write them out and not make mistakes. I made mistakes in even simple formulas, so let's hope I can not screw up this one. And I'm only writing it down because I have some points to make from it. Otherwise, it's completely confusing equation. All right, that's the first one. I'm already running out of energy. And Gabrielle, please check it while I erase this part. This one here, it's another transport coefficient. So there's a bunch of numbers that start popping up at this order that you have to compute some way. So there's this one, which we've seen before. This is the relaxation time. And this is going to be, is the funny way that the DNMR people are, a lot of people like to write eta. So this is going to be the shear, related to the shear viscosity up to a factor of 2. And these things are going to be different transport coefficients that pop up at second order. So once you go beyond Navier-Stokes, you get something called this relaxation time, which we introduced in the hand waving way over there. It's naturally sitting right here. We get eta over S, so this is coming from the eta, this is coming from the constitutive relation, but then some new terms that you didn't expect to appear. Oh, we're coming to that, yeah, that's also a good question. But I have to write the other one, otherwise the set's not complete. Right, so these are the factors of 2 that I warned you about, and some notation just so that when you go and read the Denical papers or some papers that I wrote later, you'll be able to immediately recognize those symbols and connect them to the physics constants. Yes? This one here? Here. Oh yeah, I should define that. That's a good point. Well, they're the same as what we had before. This is the symmetric traceless part, right? So that's what these brackets mean. By definition, this thing is already, symmetric traceless, but just to make it explicit, we write it again. Now, there's a way to make this formula through something called a 4-index projector. I'm not going to write it down. It's in the notes. Okay, what are all of these terms? Well, we see this kind of, these bits that we introduced in the ad hoc manner. This chalk doesn't work at all. This was our sort of naive way of restoring causality. In the limit that tau pi goes to 0, you just get some constitutive relation between these two things. And what the hell did I do here? There must be a tau pi floating around here. Just a second. I think. Yeah, sorry. I think I didn't write it correctly. So these two terms actually diverge. The rest of them are finite in the limit that tau pi goes to 0, this one. And then these, you just get the constitutive relation out of this after plugging in those relations over there. Likewise here, these first two terms are the ones that sort of naively fix causality for you and give you the limit that in 0 relaxation time that you go back to the Navier-Stokes limit. But then we get all these additional terms. So what is this one? Somebody asks, what is omega? And Francesco Beccattini will talk a lot about omega this afternoon. I'm sure he already started yesterday. It's something called the vorticity, and it's related to rotation in the fluid. So some new structure appears, and Francesco will talk a lot about that, so I'm not going to focus on it. Then, so that's hiding in here. But then we have some things where we see that pi is coupling to the Navier-Stokes level, divergence of the fluid flow, and there's some computable number, which you can actually compute. I'll show you the result in a second, what it is, and reduce this to a very simple form. Then we have an equation that's being driven out of equilibrium. Remember, theta is 1 over tau in Bjorken flow. So this thing causes a big correction to the evolution of pi. And then there's this funny thing that's coupling the shear to the bulk. And that's given the transport coefficient lambda little pi capital pi. So there's now an actual coupling at second order that exists between the two. Likewise, over here in the bulk equation, we get, in the normal terms, we get some big reaction to the gradients, which is encoded there, and then we have this coupling back to the shear. So now the shear and bulk are coupled. They're not independent anymore like they were in the original Navier-Stokes picture. Okay, I think that's all right. The good news is that we're almost to attractors. We're almost through the background material. But all right. So these equations are the DNMR, second order viscous hydro equations, the ones there in the upper, the one in the upper right-hand corner. In the relaxation time approximation, if you're not in relaxation time approximation, there's even more terms and even more coupling constants called phi 1 through phi 7. I don't remember the names of them all. But in the limit that you have this RTA collisional kernel, many of them are zero, and you get this quote-unquote simpler form of the equations. Now we're going to simplify it even further by taking the limit of our friend conformal Bjorken flow. We've already did RTA, so it's already included in those equations at second order. So I won't go through all of the steps in this case. Bjorken flow has vanishing vorticity, so the vorticity term goes away. Sigma mu nu you can just write down directly. Theta is 1 over tau. There's no bulk viscosity in conformal flows, so these terms turn off, so things get a lot simpler. But in that case, you can actually compute these coefficients that are flying around in these equations. And did I miss one? I hope not. No, I did not. Good. All right, so I erased the d mu t mu nu equal to 0 equation, but you maybe remember it in your head. It had that ideal part plus some derivatives of pi mu nu floating around. And in the end, in Bjorken flow, and maybe you can convince yourself of this in exercise sections, that in this simple case, the first equation reduces to this simple ordinary differential equation for the evolution of the energy density. Where I've written this as dt of log, you can expand this out as 1 over epsilon dt epsilon and move epsilons to the other side, but this turns out to be a convenient way to write it going forward. And then this one, we can ignore the bulk because it's 0. It reduces to the following form. Where I've now written everything explicitly in terms of eta. And then I'm going to stick with the Denical notation. And write this second term as something called beta pi pi. In practice, in RTA, that number is a weird number. It just falls in your lap. It's 38 over 21. We'll actually sketch how you can calculate that 30 over 21. It's not at all obvious. Good. So those are the two equations that in practice we could solve numerically and then obtain the evolution of the temperature along with this viscous correction. And then we could plug it into this formula that I showed you before. PL over PT is P minus capital pi over P plus pi over 2. And then you could on your own, make a plot of this pressure ratio now by solving those two coupled ordinary differential equations. And what you'll find is, regardless of how you initialize the system, you'll get some, and this is also for different eta over s, it doesn't matter, as long as eta over s is finite, you get pulled down to this system that's very high momentum anisotropy, and then it only relaxes back to 1 at very late times. Now, as I showed you in the slides yesterday, there's this funny trick that we can do, which was first released in, or at least, let's see, explained to the world by Heller and Spilinsky in a paper in 2015, where if I just rescale the time axis and write it as tau over this relaxation time, where, remember, in this RTA, that's simply 5 eta bar over the temperature, then all of these things sort of collapse onto a unique curve at late times. And there's even no spread. There's still some, this blue chalk is terrible. There's still some spread but at early times, but all of the late time behavior completely collapses. So that's the step that we want to get next, and we want to try to analytically, from this simple set of two coupled ordinary differential equations, get the attractor solution. So this is our starting point. The second order viscous hydrodynamical equations for the evolution of the energy density in the shear viscous correction. Good. So, roughly speaking, this tau over tau EQ, if we were to write it out here, it's tau times T over 5 eta bar. Right, so probably the first thing we want to do if we want to see this collapse happen is rewrite things into some sort of dimensionless variable. Right, it's a nice thing to do in physics. So the idea is to introduce a dimensionless time. In the conformal system, there's only one choice. It's T. Right, so I take the product of tau times T, and that's some now dimensionless time variable. I'm going to rewrite all of my equations now in terms of this dimensionless time. And I'm going to introduce, following Heller and Spilinsky, it's their notation, going to introduce the following new dynamical variable, which is called phi, which, if you work it out in the conformal system, you just take the d, we're a dot here, since we're in a nice Bjorken flow, is simply the proper time derivative. I take the proper time derivative here, I'm going to get a t, which I can then re-express as some energy density, and I take the derivative of this t, I can again rewrite it as a derivative of the energy density. In the end, if you do the math, you can write this particular combination in the following way, where we recognize this part of the first equation is appearing over there. So now I can sort of rewrite this equation, which is a differential equation, as an algebraic equation for this new variable phi that Heller and Spilinsky introduced. In fact, solving for dt, right, log epsilon, plugging it in here, and then just simply solving for phi, I obtain, I can rewrite, and there's a couple different ways to write this, so I obtain the following algebraic equation. So I've reduced one of the ordinary differential equations to an algebraic equation. Now there's a reverse map, which I don't want to screw up, but let me try to do the math in my head here.
Doing so, you have to get the x
Yep, it's conformal, so you can assume that, yes. And in fact, that's how you go from here to here. You have to use that to get this, and that's where the 1/4 comes from. So this was equation 1. We've now made it into an algebraic equation. And we see that phi is really related to the bulk viscous correction, right? So when phi is big, the bulk viscous correction is big. When phi is close to 2/3 in this funny variable, pi is 0. So phi of 2/3 is the equilibrium limit. And as we'll see, there are bounds on phi if you want the pressures to be positive, but we'll come to that later. So that's the first equation. Now, I leave it as an exercise, though this is, yes? Yeah, it could be you. You take a derivative here with respect to tau, that just becomes a t, which you can write as the energy density to the power 1/4. You take the derivative, the second term, it becomes a derivative of t, but since t is proportional to the energy density to the power 1/4, you can turn that into a derivative with respect to the energy density, and then when you divide by w to begin with, it all simplifies into this. Yeah, we're using the fact that t in the conformal case is proportional to the energy density to the 1/4, and that's where that 1/4 comes from, and that 4 and various things. Yeah, good, no problem. If you have a question, ask it, because usually if you have that question, probably somebody else in the room does too. This is small pi. Yeah, they're all small pi's now because, yes. If I said bulk, my mouth wasn't working properly. It's the shear correction, sorry, if I said it in. Yeah, it's the shear. In the conformal, we only have shear. Sorry, if I said bulk, my brain wasn't connecting to my mouth. Okay, so as an exercise, and I'll just state the result, you can take this second equation that's sitting here, and after some manipulations, you can rewrite it in terms of this phi variable in the following way. That's the exercise. So this is not the second equation, but that's simply this part multiplied by tau epsilon. I'm just sort of trying to guide you through how you get to the second equation. And then I take this after making that change of variables, and using this relation here, which we got from number 1, I can then rewrite the second equation in the following form. And it's not pretty, it's long. But I have to write it out. I'm sorry. Okay. Doesn't look very pretty, but trust me, it is pretty. I mean, you probably could have chosen different variable slightly than Eller Spilinsky originally chosen to make it more compact, but that's the result. And there's some notation flowing around that I now have to define. Let's leave this boxed equation. All right, so what is the notation I have to define? I define this thing called W bar, which is this original W variable up there divided by essentially the constant that's in front of the relaxation time. So that's going to be this 5 eta thing. So this is just to absorb the shear viscosity into the definition of this dimensionless time. All the plots that I showed yesterday were a function of this W bar, and it essentially, it reduces it to being simply tau over tau EQ in the end. Whereas before it was just this nice dimensionless variable, but then I have to put some extra factor in there in order to make it tau over tau EQ. There's some other weird numbers, beta pi pi. That's just 38 over 21. I'm just keeping it general because it's easier to write. Then what is C pi formally? All right, so I'm sticking with the Heller notation in this part. So there's a sort of chain of definitions that I have to present to you. So this C pi thing, in general, it's the shear relaxation time times T. And it's a dimensionless variable, but it's different than tau T. This is some sort of, physical constant. In the theory, it's related to eta bar. In RTA, it's just 5 eta bar. This is Heller and Spilinsky's funny way of writing eta bar. It's C eta. And then there's a ratio of eta over C pi, which is in the end just 1/5. But that's the way they try to write it in general, because the result that they derived was beyond RTA, and then you could plug in different numbers in different places. But for our specific example, these are the answers. But that's the general result, believe it or not, that you can find, maybe not that exact form, but it's equivalent to what they wrote in their paper. Also, what is phi primed here? Well, phi is just a function of this single dimensionless variable now. We've replaced the proper time tau by this dimensionless w. So phi primed is just the derivative of phi with respect to w. All right, so what we've done is taken these two coupled ordinary differential equations and reduced them down to one ordinary differential equation. And now we need to solve just one ordinary differential equation subject to some boundary condition. Good. So let's plug in these actual numbers for the example so it's not as big and cumbersome and scary looking. So we're going to plug in the 38 over 21 and the 1/5 everywhere we need to, and then we get down to a simpler looking ordinary differential equation. Now these numbers that pop up are not obvious. They're particular to second order viscous hydrodynamics. in Bjorken flow, conformal Bjorken flow, but they are what they are. All right, so that's the simpler version of this equation. Now, in general, this now replaces solving those two ordinary differential equations. We can pick a boundary condition for phi, and then we can solve this thing. And we could pick any boundary condition that we like, and if we were to solve it numerically, now as a function, I'll write it as a function of log of this rescaled dimensionless time. It will, from whatever initial condition we have, eventually flow to 2/3, which if you remember over there was the special case of the equilibrium limit. So eventually wherever you start this guy from, it will eventually go to the equilibrium limit. But what you'll find in practice is if you try to extrapolate all of these solutions back to zero, there's a whole class of them that simply diverge. And that's because here, if we solve for phi primed here, right, which is the derivative, that means all of these terms, they're going to be some 1 over omegas potentially floating around. And there's going to be a bunch of divergent terms as omega bar goes to 0. Yeah? So generically, for whatever, you can start here in the far time limit and try to integrate back, and you'll find a bunch of divergent solutions. But there's one solution that actually does this. It goes from the equilibrium limit, comes up, and then it saturates here at some value called phi naught. And the way formally you can obtain this, the boundary condition, is the following. We require that phi itself in the limit that omega bar goes to 0 is divergence free, and that the derivative is divergence free. So that means that this term here should go to 0. Yeah? So what we're going to require is the limit that omega bar goes to 0, that omega bar phi prime goes to 0. Now there's a way to make this even more formal in terms of what's called the slow roll approximation, where you say it's 0 plus some order depth, some order delta or something, you plug it in there and you do it iteratively. But for finding this boundary condition that we need over here, the one that's not divergent, it suffices to just require this. In that limit, what we see then, in the limit that phi goes to, W bar goes to 0 rather, we get a quadratic equation for phi. And you can solve that quadratic equation. And this particular number that pops out is tied to RTA plus the second order viscous hydro, but you find a solution. And actually you find two solutions because it's a quadratic equation. But one of them, the one with the negative solution, it actually diverges. If you try to use it, it doesn't work. So what you find is that you have to use the plus solution. So let's just get rid of it. You find this, I ruled out the minus there because it results in a bad solution. Good. Now, once you know this boundary condition when omega bar goes to 0, you can go back to the full equation that you have here and now just simply solve it numerically. You can continue this slow roll approximation. You can actually get an analytic form for this out, an approximate form, and it looks like this little step function that I show here. But to do it exactly, you just have to feed it into Mathematica or whatever your favorite way of solving an ordinary differential equation is. Because it's nonlinear, it doesn't have a closed form solution. But this thing, this solution that you get after fixing this boundary condition and then solving it out to here, that is the attractor. And what you'll find is if you start at any finite time, so omega bar naught here, with some solutions, yeah, let's leave 2/3 there. You'll find that those solutions all converge to this line eventually. And very rapidly, actually. My drawing doesn't do it justice. Yeah.
Does the variable, like the derivative of y, so how fast you approach this solution, does it make sense? I mean, physical.
You mean how fast do you approach the attractor here? Yeah, it depends on the theory. In RTA, it's an exponential approach. So you exponentially approach this attractor. So yeah, it makes sense, yeah. In other theories, people still debate whether it's a power law approach or an exponential damping to the attractor solution. In practice, it wouldn't matter if it was a slow power law because then the attractor business wouldn't make a lot of sense because if it takes you forever to relax to the attractor, then what does it matter? But if it's a fast power law or exponential, then in practice, you see that this is the underlying thing driving all the dynamics. So yeah, it's a good question, how fast it approaches, yes. The minus solution has a negative phi naught, and it doesn't connect to this late time equilibrium limit. You can never get there from the late time equilibrium limit. It's just unphysical. You just can't use it. It's not connected to reality. Now, let's see, I think up here. Look, vorticity. Vorticity. Okay, as we discussed before the break, yeah, so the other way that you can solve this if you are good at numerics is solve it starting from infinity with the boundary condition that phi is 2/3, that you have to go to equilibrium, then integrate it back, and you'll find this solution as well that way. All right, now because there's this relation, once we know phi as a function of this rescale time, we know the shear viscous correction. And once we know the shear viscous correction, going back to the first part of today's lecture, we know PL over PT, the pressure anisotropy in the local rest frame. It's the ideal pressure, P naught, plus or minus the shear correction, minus on the top, plus pi over 2 on the top. And then if you do some algebra, again, exercise, you can rewrite it in terms of Heller's phi variable. And you can quickly do the math in your head. When phi is 2/3, this is going to become 1. But in general, it's not going to be 1. And now instead of plotting in this sort of hard to interpret variable, we can now plot the attractor in terms of PL over PT, which we have some intuition for. So again, as a function of log of this rescaled dimensionless time, this DNMR solution looks like this. The attractor solution, where this is 1. And this is 0 down here. And if you, again, start at any finite omega naught, let's pick one where we assume that it's nice and perfectly isotropic in thermal equilibrium at some very early time. What you'll find is that it very rapidly goes down onto this attractor curve. If I start at a later time, it does that. And likewise, the same thing from below. I start at slightly anisotropic, I get it's a whole family of solutions that all just converge onto this line. My dotted lines are not great down here. I should have made them a little bit more readable. So what this is telling you, at least in the case of the Bjorken flow, it's like the cartoon that I showed you before. Even if you start in a perfectly isotropic initial condition, you're going to get drawn down into this highly anisotropic version of PL over BT. And now this is a very powerful statement, because remember, this funny variable that's sitting here is tau T over 5 eta bar. In general, this is, it works for not just RTA, but any version of second order viscous hydro you can throw at it. So this is a statement that's independent of eta bar. For any eta bar you put in, you'll get this curve. So it's this kind of universal thing that you can now count on in life. Now you can, based on what we wrote down, and this is another exercise. Now the exercises start flying. There's an exercise that you can show that in the Navier-Stokes limit, which we derived earlier, and we wrote down what little pi was, remember? Little pi was 4 eta over 3 tau in Bjorken flow. So it diverges when tau goes to 0. You can write down phi. Again, it's just going through this relation up here and then getting phi in terms of pi. But there's a little bit of work to do. That's why I leave it as an exercise. And this is a general result that's not just RTA, but all second order viscous hydrodynamics, and in fact, all theories. QCD does this at late times. Any kinetic theory does it. ADS-CFT does it. Everybody does it. This is a universal relation. If you have conformal Bjorken flow out here as omega bar goes to infinity, I need a color now. You'll match onto the Navier-Stokes solution. And I should probably be more nice to Navier-Stokes. It's a terrible colored chalk. Gonna have to buy new colored chalk. Eventually you'll match onto the Navier-Stokes solution. But second order viscous hydro has an attractor that goes all the way back to tau is equal to 0. The bad thing about it, and this wasn't a mistake in my drawing, it's negative. So if you believe there was some underlying kinetic theory here, this solution to DNMR attractor is already telling you that DNMR is going to have some problem at early times. It will break down. And we can now identify where it will break down for any temperature or shear viscosity. Good.
Sorry, I have a question.
Yeah.
Shouldn't that fail or you go to the bottom when phi goes to
It does, and if I've made a typo here, maybe it's plus. Yeah, I just copied from my notes. We can try to, let's see, does it work now? This becomes 4/3, right? Wait a minute, this is 9/3 minus 2/3, which is 7/3. Now it's 8/3. No. I might have made a mistake here, but it's 4/3. Okay, so maybe it's a plus here. I might have made a mistake there. I'll check my notes again. But at least this way, yeah, it does give you, it should be 1 when that the first part of your statement's correct. So I probably made a sign error writing it down there. Good. All right, so although once we left this panel, we sort of restricted ourselves to DNMR hydro. There are various different versions of hydro. There's something called BRIS. There's old Mueller-Israel-Stewart, and it's just slightly different choices of these constants in this one-dimensional ordinary differential equation. And in all of them, you find a solution that looks like this. The thing that changes is the precise boundary condition here. And if you start with Mueller-Israel-Stewart, you'll find that phi, the boundary condition's even bigger. And this problem with the negative pressures is even worse, which means it breaks down earlier. That's because they didn't include all of the second order terms. DNMR worked harder, and then they were able to improve it, but it still breaks down, but at a slightly later time than when MIS breaks down. BRIS, which is Bayer-Romachka, Sun, Starinets, and Schiff, is similar to DNMR, where it breaks down. Then the question becomes, can we come up with a solution that doesn't break down? And how do we know that this breakdown is even real? As I discussed yesterday, in some cases, PL can be negative, right? As I said, if there's some magnetic field around and you're sitting right on top of a magnet and you calculate the energy momentum tensor there, you'll get TZZ is negative. That doesn't mean space is unstable on top of the magnet. It means that you have to take into account fields in addition to particles in your description. But in any particle description, this quantity should always be positive. So what we can do is start from this simple RTA model that we had up here and solve it exactly. And then we can get the exact attractor out in a theory where we don't need to make any hydrodynamic approximation at all. It's a simple theory, but it's one that we can solve exactly. And then we can start comparing MIS, BRIS, DNMR to all of this. But before I do that, I want to introduce a way that actually guarantees that PL over PT is always positive, and as it will turn out, gives you a solution that's indistinguishable by the human eye from the exact solution. It's an approximate solution, but still, actually maybe I should do that next time so that students have a break before your lecture and you can prepare. I think it's a good place to break. So what we'll do in the next lecture, I don't know when that is we'll introduce what I call anisotropic hydrodynamics. Okay, thank you.